Okay, so we skipped this section. Well, actually, we did this section about how salt can change pH, and then we jumped down to the titration stuff because we were doing the titration on Monday. And so now what I want to do is move on to the next step with this, which is buffers. Okay, so what does that word buffer mean to you? Forget about chemistry. What does buffer mean?
Sort of a barrier.
A barrier. Okay. Anything else? Either stop something from happening or slow down something from happening. So a good buffer is a helmet, shoulder pads, shoes, knee pads, anything that would slow down the rate of impact would be a buffer. Your computer has a buffer, and what it does is your phones also have buffers. You like click on something, like a video to watch, and it takes like a moment, maybe a second, for it to start playing. What it's doing is it's building up some of the video. It's like already got 20, 30 seconds of it right away in its buffer. So then if sometime while you're watching this, 5-minute video, your internet connection cuts out or gets slow, then it uses up some of that buffer. So what it's doing is it's trying to stop you from having a delayed in your video. In the helmet situation, it's trying to stop your head from being slowed down too quickly. That's really the point. It's your helmet absorbs energy, trying to slow your head from being, trying to reduce the deceleration of your head. So the real answer for what a buffer is it tries to prevent something from happening. So in chemistry, what we're trying to do is prevent changes to whatever the chemistry is. And for this section of notes, what we're going to be trying to do is stop a change in pH. Doesn't matter what the pH is. What we would like to do is to keep the pH where it is. Don't let it move it up. We're going to use this equation right here. But we're going to go through and explain what this equation is. So what we've got here is I want to know what the pH of the buffer is that I've created. I use the pKa and I use the acid, or in this case, whatever the weak acids concentration is. And in the numerator, I put that salt anion up there and then take the log of that. So here's your Ka expression for any weak acid. I've got my weak acid, HA. It's in an equilibrium with itself and its anion. And so the products go in the numerator, goes the reactants go in the denominator. If I take this equation here and I rearrange it to make it look like that, simply just a little bit of algebra, and divide both sides by H plus, move everything around, I end up with this equation. Then if I take the log of everything, well, what happens if I take the log of H plus ion concentration, the negative log of it? That gives me pH. So if I take the negative log of this first part turns into pH. If I take the negative log of Ka, I get pKa. And then I have the log here, and then this is going to be the weak acids concentration and the salts concentration. So that's how this works. This is called the Henderson-Hasselbalch equation, and this is how a person creates a buffer. There's lots of reasons that you'd want a buffer. Any of you guys taken the anatomy and physiology class? There's some cats upstairs, about a dozen cats upstairs, dead cats that they dissect. There's also like pig hearts, livers, brains. Those solutions all have a buffer inside of them. We want to make sure that the pH of the solution stays exactly the same so that no microbes can take hold and decay those organisms, or what's left of those organisms. obviously your blood, we had that discussion yesterday or Monday about your blood needing to keep its pH exactly what it is. And so we want to make sure that our blood has a buffer, and we're going to go through that specifically. Like milk has a buffer in it. The milk's pH needs to be what it is, and it can't be too acidic or it's going to curdle the proteins. And there needs to be a certain amount of acid in it, because if it becomes too basic, again, the proteins in the milk curdle. And I mean, just dribble a little bit of vinegar into milk and see what happens. It immediately coagulates. So microbiology class, when you're like creating plates of microbes to allow them to grow, they need to be at a certain pH. And that pH could be 2, could be 12. Doesn't really matter. It's just whatever that thing lives at. H. pylori bacteria lives at pH like 1.7. So if you were going to try to grow up some H. pylori, you'd want to make sure that the buffer was around your stomach acid concentration. Okay, so here's an example of one of these problems. And so what we have is we're going to make a buffer. And so pull something up here. So I'm going to make an easy one. So this is sodium fluoride and hydrofluoric acid. So this is a weak acid. So most of the stuff stays stuck together. This is a salt of a weak acid. So why am I calling this the salt of a weak acid? It's a salt because it's a cation and an anion, a metal and a non-metal. And it's the salt of a weak acid because if I take this F and I put an H on it, it becomes hydrofluoric acid, which is a weak acid. So that's why this is the salt of a weak acid. So this is your classic buffer, salt of a weak acid and a weak acid. I put them in the container together. So why does this work? It works because, well, let's do this first. When this goes into water, what happens? The sodium fluoride. Mm-hmm. I got it dissociates. I got aqueous sodium and I've got aqueous fluorides floating around. The sodium is a spectator ion, just always a spectator ion. So it's not going to do anything. So we're just going to ignore this. So that's why this equation here that's why this equation has this negative charge on it, and there's no positive charge associated with it, because the positive thing is a spectator ion, and I don't really care about it. It's not going to do anything chemically. Okay, so in my solution, what I have are these two things. I have fluoride ion, and I have aqueous hydrofluoric acid floating around. So what happens if I put hydrochloric acid into this buffer? So HCl goes in, and what does the HCl do? It separates into H pluses and Cl minuses. Why? Because it's a strong acid. Okay, so here's another spectator ion. It's not going to do anything. Chloride's the anion of a strong acid. But now I've just added free H pluses. So the pH should drop. But what is this buffer going to do? And remember, what the buffer is doing is stopping something from changing. And so in this case, what's changing is I increase my H plus ion concentration. How does it stop that increase? So your options are this does something or this does something. This can't do anything at all. The hydrofluoric acid is a neutral molecule. It can't deal with a positive charge. The fluoride's made its one bond. The hydrogen has made its one bond, so it can't do anything. But since this is an acid, this is a base. One of the ideas of what a base is something that can give away electrons. And the fluoride ion has 8 electrons, 4 lone pairs of electrons around it. So what does this H do? It attaches to it and it turns itself into hydrofluoric acid. So you put an H plus in water and the H plus turned into an HF. That effectively removed the H plus from the water. So H plus is being added, H plus is being removed, turning into a different molecule. So what happened to the pH? It did not dramatically drop. Are we okay with that? So let's try the opposite. So I've got my fluoride ion floating around. I've got my hydrofluoric acid floating around. And to this, I add sodium hydroxide. Well, it's a group 1 metal, so it's going to turn into sodium ion and hydroxide ions. I have just increased the OH negative concentration of my system. And so Arrhenius would say, all right, this thing's a base. I've added a base to the system. So how is this base going to be buffered? Can the fluoride do anything to this? Why not? They're both negative. They would bounce off of each other. There's no chance of anything happening there. But I also have this HF. And so this H can go down here. When the H attaches itself to the OH, what does it turn into? It turns into a water molecule. So I increased the OH minus concentration. And what did this buffer do to it? It got rid of the OH minus. It turned it into water. Now I've got another F minus floating around. So really, I've just increased the concentration of that side of the buffer. Are we okay with that? Every one of these buffers works the same way. Something has an H that can come off, and something's got a place for an H to go. The salt of the weak acid is that anion will have extra electrons on it, so it will be able to accept H's. And the weak acid has an extra H on it, so that H can come off and then neutralize a hydroxide. And so that's how a buffer works from both the acid side and the base side. Any questions about that? So let's go to some calculations. So we'll do this first one just so we can see what the calculation looks like, and then we'll get more specific with it. So somebody's created a buffer. The buffer, I want to know what the pH of this particular buffer is. The buffer is a 0.75 molar acetic acid solution and a 0.5 molar sodium acetate solution. So what I've got here is CH3COOH and CH3COONA. So that's a salt, hits the water, the Na pops off. And so I really don't care about the Na part of it. It's just a spectator ion. So I've got this negative anion floating around, and it's weak acid counterpart. Does this want to be floating around in the water by itself? Let me ask a different question. Does this want to separate into H pluses and acetates? It's acetic acid, but give me a classification of what kind of molecule it is. What kind of acid is it? It's a weak acid. So what do weak acids like to do? Chill. They like to stay stuck together. They like to have their H attached to their anion. So what's happened to the acetate below? It lost its H. So what would it like to do? It would like to get its H back. So it's actively searching through the water, looking for any excess H pluses that are floating around. And what's the acetic acid above doing? It's floating around doing what? What do acids and bases do when they come in contact with each other? They make a salt and water. They like to make a salt and water. They want to do that reaction. So The top one's running around looking for OH molecules to neutralize. The bottom one's looking around for H pluses floating around to neutralize those. So what we've done is we've created this little buffer. This number here is the pKa value just off of that chart. So when you get a question like this on the homework, I'm just expecting you to go to the notes and look at that chart. And by that chart, I mean, or table, I mean this guy right here. If you got a question like this on the exam, you would have that table fully ready to go to use. Okay, and so what I do is I take the concentration of the weak acid and put it in the denominator. I take the concentration of the salt and I put it in the numerator, and then I do the math. Are we comfortable with this, Matt? Everybody want to break out a calculator and do this? Tell me I mean, I gave you the number right there, 4.57. I want to make sure you can get 4.57 on a calculator. Yeah, make sure you can shove that into the calculator and get 4.57. There's some parenthesis issues associated with it, and people aren't usually using log base 10 calculations, so. 4.57. That's the pKa. So that's its Ka value. They took the negative log of its Ka value. So let's look at that for a second. 1.74 times 10 to the negative fifth. That's its Ka value, okay? So let's forget about the 1.74 for a second. What would happen if I took the negative log of 10 to the negative fifth? 5, because it was negative log. It's just going to be 5, right? But it's not just 10 to the negative fifth concentration. There's a little bit more in it, right? It's 1.74. It's not 1. So that means it's going to be a little bit more acidic. There's a little bit more dissociation of that weak acid. So the pH number isn't going to be 5. It's going to be a number a little less than 5. And so that's why the pKa number is 4.75. You okay with that? So if you see a pKa number of 6.2, what that's telling you is its Ka value has a whole number exponent of 10 to the minus 7th, but then the number in front of it isn't 1. It's going to be a number like 8 or something like that. All right, so why did the number go from 4.75 to 4.57? Just purely mathematically. There's more acid there, right? Just that's a chemical way to think about it. Chemically, I have more acid in this than I have salt, and the salt is the base. So of course it's going to be more acidic than basic. What would happen if I had the exact same concentrations, like 0.75 in the denominator and 0.75 in the numerator? What happens when you've got the same number divided by the same number? One number divided by itself. It's 1. What happens when you take the log of 1? What's the exponent? What's the scientific notation value for 1? 1 equals 1 times 10 to the 0. Are we okay with that? What happens if you take the log base 10 of 0? Or log base 10 of 10 to the 0? What do you get? 0. Does that make sense? So if these two numbers are equal to each other, then this entire term equals 0. And so then your pKa, your pH is equal to your pKa because your salt and your base are exactly the same concentration. Are you good with that? So mathematically, it makes sense that the number is smaller because this numerator is a smaller number than this denominator. So that's why this value is going to be a number a little bit less. If when I do this, when I take 0.5 divided by 0.57, I'm going to get a number less than 1. So it's times 10 to the number is times 10 to the negative something or other. And so if I take the log of that, I'm just going to get a negative number. And so in this case, the negative number is 0.18, right? 0.5 divided by 0.75 is 0.18. And I know that because if I subtract those things off, if I subtract 0.18 off of 0.75, I get 0.57. Are we okay with that? Okay. So I want us to do this problem, and these two problems I'm going to put together, and I want us to make sure that we can be able to do both of them because you're going to be asked to be able to do these questions. So what happens if I add some acid or base to pure water? I want to know what happens to the pH. So I've got 40 milliliters of 0.25 molar sodium hydroxide. I add it to 550 milliliters of water. What's the resulting pH? So how do I calculate pH? pH is equal to what? The negative log of what? Concentration of H plus. You okay with that? All right. So I need the concentration of H plus. Well, I don't have any of that. I'm going to have to get that. So I need to do a couple of things. The first thing I'm going to want to do is 0.25 moles per liter, and I've got 0.04 liters. That's 40 milliliters. So that's going to be 0.1. 0.01 moles of OH. Negative. All right. So I know how many moles of hydroxide I've got. So I need to know the concentration of that OH. All right. So I've got 0.01 moles of hydroxide divided by 0.59 L. Where did that come from? Because I have to know the volume once they've been added together, right? The new volume is 590 milliliters. It's not 550 anymore. It's 590. So that corresponds to 0.59 liters. And so now 0.01 divided by 0.59. And so I get 0.0169. That's good enough. Moles per liter hydroxide. Okay. So there's my hydroxide ion concentration. So what can I do with, how do I get myself from hydroxide ion concentration to H plus ion concentration? Do you remember that? Yeah, that's exactly what we do. So I'll take the negative log of that. So negative log of 0.0169. Negative log 0.0169, close parentheses. I get 1.77 for my, this is my POH. All right, so 14 minus 1.77, and I get So 550 milliliters, it's about this much water, a little more than half of this container. And I added 40 milliliters, so just a little bit more. And the pH went from being 7 to being 12.3 or 12.23. Do you want to guess what kinds of things have that high of a pH? Do you remember? So this is household ammonia, and we're over here. So this is Windex pH, and we're 10 times more concentrated than Windex pH, just by adding a low concentration of sodium hydroxide to a solution that's more than 10 times bigger than it. And the pH still went from 7 up to 12 something. So what's the difference between the water's pH beforehand and the water's pH after the addition of the sodium hydroxide? It's 1, 2, 3, 4, 5 plus orders of magnitude. So you're looking at nearly 100,000 times more basic by adding that small amount. So this would kill most anything, microbe, not microbe, whatever, anything living wouldn't be able to handle that pH change. Okay, so now what we're going to do is we're going to do the same situation, but this time we're going to add it to a buffer. And we're going to see what happens once the buffer's been added. Put this on a blank page, make it easier. Okay, so we need to do a whole bunch of things. And so the very first thing we want to do is we want to calculate the pH of the buffer. Okay, and so the pH of the buffer, this is acetic acid again, so it's 4.76 plus log of the weak acids concentration, which is 7 molar, and the salts concentration, which is 0.04 molar. So, oh, I did that completely backwards. My bad. .04 molar on the bottom and 7 molar on the top. So from our last problem when we did this, tell me what's going to happen to the pH. Is it going to be a number bigger or smaller than 4.76? Is it going to go up or down? Just look at the numerator and denominator. The numerator is a lot bigger. So that means this number is going to be a number bigger than 1. So when I take the log of that, I'm going to get a value that's larger. That's going to be a positive value. I'm going to add that to my 4.76. The other way you can look at this is my base, and this is my acid, and I got a lot more base than acid, so the pH is going to go up. So let's make sure we can all get this number, 4.76 plus log of what'd you guys get? It's 7.003, so it's effectively of a pH of 7. So what we have is pure water from the last problem had a pH of 7, and now we've got a buffer whose pH is 7. Okay. So how do I figure out what's going to happen with the buffer's concentrations? Because again, what we're trying to do is figure out pH. And so what we need to do is, how are these two things affected? So we're going to build a construct, a mathematical construct to deal with this for us. So the first thing we need to know is we need to know the moles of everything. So this 0.25 moles per liter and 0.04 liters. And so this was 0.01 moles of the addition, the hydroxide. Now I want to know the number of moles of both my acid and my salt of my weak acid. So I've got 0.04 moles per liter. And this is 5.55 liters because it was a 550 milliliter buffer. And so, 4.55. And so this is 0.022 moles. I'm going to write HA. What is HA shorthand for? HA is short for weak acid. So it's H, and that's this H here. And then the A is the anion, the acetate. And so down here, I've got a charged polyatomic ion. So that's why it's just A. So it just makes it easier than us writing out all the letters and numbers for acetic acid. So my weak acid's number of moles is 0.022. And so let's see, I've got a concentration of 7 moles per liter times 0.55 liters. So 7 times 0.55. And so this is 3.85 moles of the base of A negative. So now I know the number of moles of my contaminant, in this case, the hydroxide, the thing that's trying to raise the pH, the number of moles of my weak acid portion of my buffer, and the number of moles of my my anion from my buffer. So I need to know what's going to happen with this. When this goes in, which one of these two things is going to react with the hydroxide? Those are options. Either A negative reacts with OH negative, or A negative reacts with HA. So which one of those reactions is going to actually occur? Why can the first one not happen? They're both negative. They're literally going to bounce off of each other. Like trying to shove two sides of a North magnet together, they're just going to push off. So this can't happen. What is going to happen is this is going to come off and react with that. I wrote that wrong, didn't I? Maybe that's why that was confusing. Sorry about that. That's better. This H is going to come off and react and make water. Okay, so when this goes in, I'm going to lose some of my acid, my weak acid part of my buffer. I'm going to gain a little bit more of my anion, but I'm going to lose some of my weak acid. So how do we mathematically deal with this? So this is the way chemists have determined an easy way to do this. This kind of thing gets used for lots of stuff, but we call this an ICE table. And the ICE stands for initial, change, and then equilibrium. So initially, I have 0.022 of my acid, and I've got 3.85 of my anion. That's what I'm starting off with. Then I add the sodium hydroxide to my solution, And which one of these things did we say the sodium hydroxide was going to react with? The HA. So that means I'm going to lose some HA. How much am I going to lose? Well, I'm going to lose exactly the amount of hydroxide that was added, so 0.01. And when that reaction happens, the HA is going to turn into A negative. So this number is going to go up by 0.01 as some of the, in this case, acetic acid turns into acetate anion. So then I just do some addition and subtraction. So this turns into 0.012, and this turns into 3.95. We okay with that? So then I can use my Henderson-Hasselbalch equation again. So pH is equal to 4.76 plus log, and I put the acid in the denominator, so 0.012, and the base in the numerator, 3.95. And then see what this looks like, 4.76 plus log 3.95 divided by 0.012, close parentheses, equals. Okay. So my new pH equals 7.3. So what happened when I put the sodium hydroxide in the pure water? The pH goes from 7 to 12.23. And this time it goes from 7 to 7.3. So did the buffer buffer? Yeah, this is how buffers work. They have the salt of the weak acid and the weak acid. I put them together, and one of those two things is going to react with whatever I add. If I add a base to it, then the weak acid's going to react with it. If I add an acid to it, then the base is going to react with it. What they're effectively doing is removing that substance from the solution. So how was all that? You ready to take the test? Pop quiz.
Oh, what is C and D stand for? Nice, because this is the first one with initial.
Change in equilibrium. Do you want to do some of these? Yes, probably. Okay. Feel free to yourselves. I'll be right back. We got a before and after value. How about a before value? Oh yeah, absolutely, because it's propionic acid. So the value is 4.86. So before we even do the math, is the 4.86 going to be bigger or smaller? Bigger. I know that because my numerator is bigger. I've got more base, so then the pH is going to be. So then the number of 5.19 pops out. I'm okay with that. Okay, so I make my buffer, and my pH of this particular buffer is 5.19. So now I'm going to do an addition. I'm going to see how that addition is going to modify the pH after the change. So what are we doing? We're putting in a 0.4 mole per liter hydrochloric acid, and we're going to put in just 0.015 liters, 15 milliliters. So 0.006 moles of H plus is being added. And so the concentration of my weak acid is 0.25 moles per liter. And how much do we have? 750 milliliters for 0.75 liters. So 0.2. So I got 0.125 moles of HA. And so we've got 0.53 moles per liter, and again 0.75 liters. So 0.53. I get 0.1325 moles HA. I'm going to go ahead and make an ice table again. So initially I've got 0.125 here, and I've got 0.1325 here, 25 here. Okay, so I'm adding an acid. Which one of these two things is going to be decreased? The HA or the A negative? What is the acid going to react with? And your options are propionic acid or the salt of the propionic acid. Your options are the H plus reacts with the A negative or the H plus reacts with the HA. Why is the second one not going to happen? Because it's already an acid. An acid isn't going to be more of an acid. So I'm not going to use an acid to react with an acid. I am going to use the anion because it's negatively charged. It's got excess electrons, so it can absorb that proton. It can accept that proton. So I'm going to lose A negative. So how much am I going to lose? I'm going to lose 0.006. And so I'm going to gain that exact amount in acid. As this A negative gains in H, it turns into HA. So minus 0.006. Is 0.131. And so then we'll do the Henderson-Hasselbalch equation again. So I've got 4.86 plus log 0.1265 divided by 0.131. So 0.65 plus log close parentheses equals, and my new pH is 4.84. So it was 5.19 and it dropped to 4.184. So it dropped, but not that much. Let's see what would have happened if I would have just dropped it into pure water. So I'm going to take my 0.006 concentration H plus divided by, in this case, it'd be 0.765 liters. So 0.006 divided by 0.765. So that's 0.007843. And if I take the negative log of that, the pH equals 2.1. So I get a change of, I don't know, 20, or not 20, 8 times more concentrated, versus I get a change of 1,000 times more concentrated. Without the buffer, the pH drops, and the concentration of acid goes up by 1,000. With the buffer, it goes up by like 8 times versus 1,000 times. Okay. How are we feeling about those? Go for it.
My mole values were different.
Your mole values were different than mine? Did I punch myself into the calculator wrong? You guys stopped me ahead of time. Oh, yeah.
They want to stop us going on a roll.
This is supposed to be 875, right? And this is supposed to be 0.3975. Okay. Definitely math errors there. Yeah, sorry. So you get an eraser.
Each something with slightly higher. Like 5.
So this was supposed to be 0.1875. This is supposed to be 0.3975. And so I subtract off 0.006 and I add 0.006. So this becomes 4.015. Just, oh wait, no, not subtract, sorry. 3.3915. There we go. And then this one is 0.1935. Okay. All right, so let's try that again. 0.487 plus log 0.3915 divided by 0.1935. Oh yeah, that's even better. 5.17. So it went from 5.19 all the way down to 5.17. So the buffer definitely did its job. Use the right terms. Okay, thanks. Okay, where? So I'll give you guys an opportunity to, practice that on the homework. Buffer problems. All right, so I told you before that we talk about the blood. I keep getting these things. All right, so here we have. So the individual chemical reactions that happen, and the first one's actually not a chemical reaction, just a dissolve. Carbon dioxide as a gas gets dissolved into water. So you create carbon dioxide in your cells. This carbon dioxide becomes aqueous. Aqueous carbon dioxide chemically reacts with water to turn into carbonic acid. So what we have is an equation where carbonic acid reacts with water and turns into hydrogen carbonate and hydronium ion. And so overall, if I take all of these reactions together, here's the acid part of my blood. Here's the base part of my blood. Here they are in form where they neutralize each other. And then here's the exit part. So where does the CO2 gas come from? Exhaling it or not exhaling it. So if you hold your breath, your body keeps metabolizing glucose, and the concentration of CO2 goes up. Okay? When the concentration of CO2 goes up, what would Le Chatelier say is going to happen? So I got a bump in CO2.
Which point is he out of the free in the chronological order?
I don't know what that means.
When you think of the acid base,
The other guys.
This is an acid base. This is Le Chatelier, the last thing we talked about last quarter, which was the equilibrium stuff.
we can go back towards the hydronium.
Correct. So what Le Chatelier says is if I've got an equilibrium and I disrupt the equilibrium tries to get rid of that disruption. So what's the disruption? The disruption is the CO2 concentration going up. So this goes up. So how can I get rid of this excess CO2? I can make the reaction go this direction, right? Consume CO2 and water, and I can make water and carbonic acid. Well, now these two things have gone up. So what does this equilibrium do? It shifts this direction. And this goes up and this goes up. Effectively, what I've done is I've increased the acid in my bloodstream. So you hold your breath and the acid concentration of your bloodstream goes up because you can't get rid of the CO2. So instead of you getting rid of the CO2, more of it chemically reacts with the water to make excess H+. Okay with that? So how does your body deal with this? What's the most important thing for you if you had a problem with an increase in acid or increase in base? The answer is the same for both of them. So let's say for some reason I had an increase of H+ in my bloodstream. This reaction is going to shift this direction. It's going to shift this direction, and I'm going to have an increase of CO2. How do I get rid of it? I exhale. I literally breathe. If you have a problem with the pH of your bloodstream, what do? You breathe. Literally, you breathe. You exchange the gases in your bloodstream with the gases that are in the air. And so if the acid concentration in your blood goes up, you actually exhale more carbon dioxide than you normally would. So why would the concentration of CO2 in the bloodstream go up, the acid concentration go up, you're working out really hard. So most people are like, well, I'm working out really hard, so I need to bring in more oxygen. Super important. But what also is important? I need to get rid of the byproduct that I created because it's toxic to me at higher concentrations. So it's not just an inhale. It's not like you can just keep breathing in and expect everything to be fine. You can have high oxygen concentrations, but if the acid concentration in your bloodstream is too high, that's going to kill you just the same. That woman that got put underneath the ice, that cold water, remember that homework problem from last quarter? Why didn't she die? All the metabolism slowed down. She did not jack the CO2 ion concentration up. Her bloodstream was able to manage the small amount of metabolism that was occurring for those 40 minutes where she wasn't breathing because she wasn't metabolizing stuff because her body had turned itself off. What happens if your bloodstream becomes too basic, and so the acid value starts to drop? Instead of breathing out the CO2, you don't breathe out the CO2. You exhale, and instead of spitting out the normal amount of CO2 that you exhale, your body holds on to it. You do nothing. Like mentally, you don't think about it in any way. It's just your body's like, well, I'm not going to do that. I'm going to leave it here. It's going to stay inside my bloodstream because I'm going to combat my increasing hydronium ion concentration, the increase in base with CO2, which can turn into hydronium ion and cancel it all out. So it's literally getting somebody to fresh air. Somebody who's got an issue with acidification or alkylation of their bloodstream, you get them the fresh air and you let them breathe. If they can't breathe, you get a ventilator on them as fast as possible. Even as just one of those squeezy things, or do compressions and breaths. Well, not compressions, but do breaths if they're not breathing. So all you're trying to do is get the gases that are in there, the correct ones to come out, and the other ones to go back in, swapping out gases for what needs to be in and out. And so the buffer calculation kind of looks like all of these things in the denominator and the hydrogen carbonate in the numerator. If an EMT comes on a scene and a person isn't breathing, the first thing that they're going to do besides start compressions and breaths is fill them like directly shoot baking soda into their veins. What's the baking soda going to do? This is the base. It's also can be an acid if it needs to be. So the buffer for your bloodstream is really just hydrogen carbonate. So how can one thing be a buffer? So I am hydrogen carbonate. Let's say excess acid gets added to the system. What can the hydrogen carbonate do? It can just grab a hold of it and turn into HCO3. What happens if the opposite situation happens and all of a sudden there's excess hydroxide ion? It can give that H to turn this thing into water. So that's why it's the perfect buffer system for your body, because all by itself, the hydrogen carbonate can donate an H to get rid of excess hydroxide ions, and it can accept an H to get rid of excess hydronium ions. Okay, the last thing on this set of notes is me just showing you a couple of reactions that happen in everyday life that are acid-base related. So that first one, I think we talked a little bit about it. Do you guys remember me talking about what a pain in the butt hydrofluoric acid has been through the years? What was hydrofluoric acid's issue? Why was it a problem for chemists? It dissolves glass, and this didn't exist yet. Plastic didn't exist. So if it dissolves glass, what do I store it in? I store it in a wood container. It eats through wood too. So how did they actually store hydrofluoric acid? They took a glass container and they dunked it in molten wax. The entire inside of the flask was coated with wax, and then they put the hydrofluoric acid in there, and it wouldn't chew through the wax because the wax is nonpolar. And I mean, that's the reason that it wouldn't chew through plastic, because the plastic is nonpolar. So the issue is the hydrofluoric acid just needs to stay where the wax won't melt. If it got hot, the wax melted and then it started chewing through the glass container. So what do we use hydrofluoric acid for? We can use it for that. Can we see what that is? Etched glass. So you basically you do one of two things. You either use some sort of really good tape and you tape out the object, or you paint wax onto the glass. And then you smear hydrofluoric acid, sort of like a paste over the top of it, and you just wait. And then you wipe it off, and it will coat, it'll start chewing away on the top part of the glass. It doesn't do it in a systematic manner. It's very chaotic. So when the light tries to come through the glass, all of the lined up light splits in different directions. So light is coming through, but I can't see what's on the other side because the light got chaotic as it came out the other side of the glass. So bathroom windows, any of those opaque windows, that's all that they've done. They just added a little hydrofluoric acid to the exterior. They basically roughed up the exterior. It's the exact same thing that would happen if you went and use some really good sandpaper on the exterior of a window. You're just messing up the surface so it's not flat. So when the light comes through, it gets scattered. So that's what hydrofluoric acid does. It scatters light. That's what happens to the glass once it's been etched, basically, with the hydrofluoric acid. When I was living in Pennsylvania, somebody was taking hydrofluoric acid and spreading it over the windshield of police cars, right where the person would look through the window. Got like 5 police cars before he got caught. He was upset about getting a ticket. And so he went to Michael's Craft Supply and bought himself a little jar of hydrofluoric acid paste, paper towel. That's it. Walk away. In 15 minutes, it'll be so etched that you won't be able to see through it. Do you guys know how much a windshield on a police car cost? And granted, this was 25 years ago. This was in the late 90s. $10,000. So he was on the hook at that time for $50K plus destruction of public property. So wasn't the smartest move. But it's easy to get your hands on. I mean, you can go to Joann's Fabrics and buy yourself some and, etch something. I mean, I wouldn't do it because I'm a terrible artist, but if you want to draw something, it'll work. All right. And then the other one here, I've got marble and sulfuric acid from acid rain. It turns into calcium sulfate, which is soluble, and then water and CO2. So if you've got a marble statue and it's being exposed to the atmosphere, it will dissolve. Have you guys seen, anybody been to Europe? Yes, no? Anybody been to Vegas? No? Okay. Well, if you go to Vegas, go to the Venetian. Okay. So the Venetian it's a casino and hotel that they've taken a bunch of Italian art from like Venice, and Greater Italy and brought all that art or have it completely recreated. And so it's magnificent. It looks basically exactly like the original that are in Europe look. But the issue is they don't look like they did when they were made. So if you look at the statue of David from Da Vinci, everything is kind of smooth, but that is absolutely not what it looked like when he made it. But it was left outside. And so even without present day pollution, um, CO2 in the air that's just naturally in the air from us breathing will produce a certain amount of acid rain. So rain's pH is a little less than 7. So even though it's, right as rain, it's still a little acidic. And so what ends up happening is all the really sharp features, the corners and the edges, dissolved off over hundreds of years. So now it's, covered and it's got buffers and whatnot. So that can't happen to it. But it doesn't look exactly the way it used to. If it was here today, it would be phenomenally sharp. Like if you had sent in an artist to paint it with skin tones and hair color tones and whatnot, it would look like a human. Like that's, I mean, really big human because it's huge. But regardless, it was so unbelievably realistic that you wouldn't have no idea that that's what you're looking at, like those really well done wax figures. The other things that are in Europe, like the Pantheon, the Roman Colosseum, and things like that, they don't look like they did before because they are slowly dissolving. And Greece itself is Greece and Rome are particularly problematic. Greece in particular, because it's kind of like Los Angeles, where the city is on the sea, but there's a mountain range right behind it. So all of the exhaust from vehicles persists inside of that little cove and stays there a lot longer. So the rain's pH is way low. It's like 4 something or other. And so when that comes down, it just starts bubbling away the Pantheon and the Acropolis and all of those things. And so a lot of those structures are not nearly as structurally sound and magnificent as they were at one point, simply because acid rain happens and it chews away at marble. All right, that's all I got. I'll see you guys on Monday.